So far, we have seen how the nature of the initial conditions, as specified by the density perturbation spectrum, and the nature of the dark matter that determines the damping mechanisms, govern the formation of the large-scale structure. Now let us look in a little more detail what happens to those density fluctuations in the early universe. During the radiation-dominated era, fluctuations do not grow, and the density field is dominated by the radiation and the matter is tightly coupled to it. However, after the matter domination begins, the fluctuations could grow. And the crucial quantity here is the Jeans length, which you may recall from learning about star formation. Essentially, the pressure suppresses collapse of fluctuations at all scales smaller than Jeans length. This formula is given here. Physically, the way you can think of it is the Jeans length is the size of the collapsing cloud where sound waves can cross before it collapses. In a radiation-dominated universe, Jeans length is very close to the horizon size itself. However, after the matter domination begins, it peels off and becomes smaller. The physical reason for this is that speed of sound drops because it's dominated by matter, not radiation, and fluctuation can start to grow. This is schematically shown here. The diagonal line shows the mass enclosed within the horizon. It grows in time because the horizon grows in time. And the Jeans mass is very close to it. At the time of radiation matter equality, the curves begin to split, and Jeans mass stays almost constant until the recombination, whereas the horizon mass keeps growing. At the time of the recombination, the Jeans mass drops precipitously by many orders of magnitude, roughly from superclusters of galaxies to scale of globular clusters. And so the key points about the growth of fluctuation is that always the horizon scale determines the characteristic length of the fluctuations. After the radiation matter equality, baryons are still interacting with the radiation field and interacting with it through Thomson scattering. The density perturbations show us the baryonic acoustic oscillations that we discussed earlier. Those are, of course, responsible for the Doppler peaks in the power spectrum of the cosmic microwave background. However, after the recombination, fluctuations can grow, and essentially baryons fall into the potential wells defined by the dark matter perturbations. Schematically, this is shown here. The density contrast does not grow until roughly matter and radiation equality. At that point, the dark matter fluctuations can begin to grow in contrast, whereas the baryons stay coupled to the radiation. After the recombination, the baryons are free to fall into the potential wells defined by the dark matter perturbations, and soon enough, they become equal. A more detailed computation is shown here. This shows the actual baryonic acoustic oscillations as they would appear, and those will map into the peaks of the Doppler peaks in the cosmic microwave background. So here is the power spectrum of density fluctuations. At the very large scales, it is normalized by using the cosmic microwave background. Those are fluctuations that go beyond the horizon, and it is the Harrison-Zedovich spectrum. Then there is the rollover due to the damping, as predicted by the cold dark matter theory. And there are, of course, the baryonic acoustic oscillations. The data points here show the galaxy clustering power spectrum scaled to the appropriate size. It does not follow exactly the theoretical prediction, and this is due to the nonlinear effects of merging and hierarchical assembly of galaxies. As you recall, the observations of microwave background confirm this theoretical picture to exquisite precision, so we know that this is roughly what happened in the early universe. So what happens after the recombination? The density perturbations continue to grow. They're already imprinted in the dark matter. The baryons soon follow. Baryons fall in those potential wells, and as they do so, they will start dissipating energy. Essentially, gas clouds keep colliding that will inevitably cause some shock heating and energy dissipation. Later on, there will be things like star formation and energy input by stars, or black holes in form of active galactic nuclei. Simulating these in detail is at the cutting edge of our ability to model universe in computers. but we can still make some progress on that. Now, the key point here is, as you recall, the transition from simply gravitationally bound fluctuation to the one that's fully virialized, meaning matter is just rearranged due to the gravity, there is no energy dissipation per se, leads to a collapse by a factor of 2, because the ratio of kinetic and potential energy changes by a factor of 2, and potential energy is inversely proportional to the characteristic size. So the density contrast that can be achieved due to dissipation-less collapse is only an order of magnitude, cube of 2, 8, or close to 10. In order for density fluctuations to achieve higher density contrasts, energy must be dissipated in some way. This process is sometimes called cooling. A good physical mechanism for this to happen is inverse Compton cooling of hot gas on cosmic microwave background photons. This really only becomes effective at redshifts less than roughly 100, because before then the photons are too hot for them to act as an effective coolant for the gas. To quantify this, we will introduce the concept of the cooling time, and that's simply the energy that needs to be dissipated divided by the energy dissipation rate. So it has dimensions of seconds. Plasma physics gives us the formula for this, which is shown here. And there is a function, lambda, which is not to be confused with cosmological constant. It's the cooling function, and its value depends on the density and temperature and composition of the material. So the key question here is the relationship between characteristic cooling time, the gravitational or free fall time, and the Hubble time. If the cooling time is shorter than the free fall time, which we defined earlier, then objects will condense faster than they would through just gravitational collapse alone, reaching higher densities. If, on the other hand, both cooling time and free fall time are greater than Hubble time, objects simply cannot form. Here is what cooling curves for plasmas of appropriate chemical composition look like, shown as a function of temperature. The relevant range of chemical compositions is from pure hydrogen and helium, which is primordial gas, through all the way to solar composition gas, which is produced by stellar evolution. So somewhere in between is all the relevant range. So objects inside the cooling curve can cool faster than they can fall together due to gravitation alone. And outside of cooling curve, they cannot cool as fast, and only gravitational collapse will matter. Now we can recast the cooling curve to be shown in the temperature density diagram. Like most thermodynamical quantities, it can be expressed as a function of these two variables. And since the Jeans mass is also a function of density and temperature, the lines of equal Jeans mass correspond to diagonal lines on this log-log plot, and they're shown here. You may notice that characteristic mass of galaxies, 10 to the 12 solar masses, goes right through the region where cooling would be dominant, whereas characteristic masses of clusters of galaxies, something like 10 to the 15 solar masses, are outside of that region. So to bring this point again, as a density fluctuation collapses, two things can happen. If it cannot cool faster than it collapses, then it will be just pure gravitational collapse on the free fall timescale. If, however, it does cool faster than it collapses, then it will inevitably fragment into smaller pieces, which then later may merge. So here is the cooling diagram again, and this time shaded regions indicate where objects of different kinds are. Remarkably enough, galaxies of different Hubble types occupy region inside the cooling curve, and groups and clusters of galaxies occupy region outside. You may recall that galaxies are overdense by about a factor of a million, whereas the virial collapse in an expanding universe can only achieve contrast of the order of 100. And indeed, we do believe that galaxies form through dissipative processes, and whereas groups and clusters in large-scale structure are product of dissipationless, purely gravity-driven collapse. So let us recap the key ideas of structure formation. Structure formation grows out of density fluctuations in the early universe, which can grow under their own gravity, accreting more material, and through merging. The initial conditions are often described using a power spectrum of the density field. And the one that is often used is power law dependent power spectrum with an exponent of 1, also called Harrison-Zildovich spectrum. The role of dark matter is essential. Dark matter fluctuations can grow before baryons can actually follow, which is why it's possible to actually have the structure that we can see. In some sense, dark matter seeds the large-scale structure prior to recombination, and after the recombination, baryons, the visible material, falls into those potential wells. Various damping mechanisms, say photon diffusion or sound waves, erase small-scale fluctuations. The nature of dark matter determines which mechanism will be at play and therefore how many of small fluctuations will be left. The observations show that cold dark matter, composed of massive particles, does fit all of the data, whereas the hot dark matter, composed of light relativistically moving particles, say as massive neutrinos, simply does not reproduce the observed picture. And the topology of the density fluctuations will always go from triaxial blobs that first collapse into the sheets, which then collapse into filaments, which then drain into quasi-spherical blobs like clusters. An important thing to remember is that, as shown through a spherical top hat model, the simple virialization, dissipationless collapse of a fluctuation in an expanding universe can reach density contrast of 200. This is more than what would happen in non-expanding universe, where only a factor of 8 would be achieved, because the surrounding background also expands while the perturbation collapses. Free fall timescales, that is, in fall just due to the gravity with nothing to oppose it, indicate that for galaxy scale fluctuations, the formation will be on the scale of hundreds of millions of years, whereas on scales of clusters of galaxies and large-scale structure, formation will be on scales of billions of years, and that does correspond to observations. Just as in case of star formation, here in galaxy formation, Jeans length or Jeans mass are key concept. They determine the scale of fluctuations that can actually grow or fragment into smaller ones. The Jeans mass is essentially mass within horizon prior to the radiation matter equality, becomes constant after that, and then drops precipitously at the time of the recombination. Cooling is the key concept, because in order to achieve higher density contrast, energy must be dissipated, which is known as cooling. And galaxies form largely through dissipative processes, whereas large-scale structure is formed dissipationlessly, purely through gravitational collapse and assembly. Next, we will see how the nonlinear processes of structure formation are simulated using computers.